Hope everyone can see my slides. Okay. So
Yes, sir.
in the last class, so we discussed about the MPI. So MPI is actually message passing interface, and you can run the MPI program on multiple machines. Okay. So and this is very simplistic. How you can compile and run on a Linux machines. This is for standalone machine. Also, you can do the things. But if and you can configure suppose you configure the MPI program for multi computers, then you can run MPI program on multiple computers. Okay, so how to configure? So this is not part of the course, but we can configure on multiple machines. How to configure? If you want, you can. I can refer some what I can say resources how to configure MPI on multiple computers. Okay, so mostly, so in general we do configure in Linux. Okay, so use NFS and NIS. Okay, so network information system and NFS, network file system, we mount all the machines will have same homes. So user will be logged to one machines and he can see other machines. Okay, and his login information will be also shared with all the machines. That means there will be one home and one login in all the machines. And we need to set up SSH auto login thing. Then automatically it will actually initiate the MPICH, and you need to add into MPICH. So this is the way you can configure the multiple messages, but we are not going detail about that. How to configure this, but how to program, like this you should know. So we have permission messages. MPI already configures, and most of the high performance system, whatever we use, we write MPI code. Okay. So message passing paradigm. So message passing program are actually it's not a shared memory access. It is distributed memory access, and each processor see different memories. Okay, so different memory systems, and they communicate through communication network. Okay, so we can run the MPI program on parallel processor, different machines itself, not in the same machine, but in a different machine. And typically, single program operating on multiple datasets, the variable of each subprogram have same name but different locations and different data. So with example, you can see that thing. So all value are local to the process. So suppose you have one program and you create multiple copy of that program. Then what will happen? So you are creating multiple copy of the process. Okay, multiple copy of the same process. That means different process, all local variable have different memory. And they communicate by a special send and receive routine. And in the SAM machines, so it actually goes through pipe. So this is very simplistic examples. Every process of a MPI program are different. So I single persons you do. So touch your nose by left hand. I touch your head by right hand. That means this kind of instructions we can give. Hi, all persons of this I'll do touch your nose kind of things. So ask everyone to do. This is collective one. Then once ask one person to do kind of thing. This way we can organize the MPI program. But how we'll do in real MPI program? Let's see. Okay, and data and work distributions to communicate. Gather MPI process need to identify using rank. So in general, so we run multiple MPI program. Okay, multiple MPI program. Whenever you write MPI program, so it creates multiple process. Okay, and each process of a bigger MPI program actually identify with a number. So all distribution decisions are based on the rank and which process work on which data or which process work on which part of the program. Okay, that also you can see. So one thing is which process work on which data, that also fine, or which process work on which part of the program, that also we can define. So this is a single program, multiple data. So very simplistic model. So same program run on each processor using different process, and MPI allow MPMD also. So multiple program on multiple data. So but the some vendor may be restricted to SPMD. The MPMD can be emulated using SPMD. So how we can do? So that thing we can see. So suppose this kind of code. So let me change to pointer. So this kind of code. So in this case, if my rank is less than X, then do oceans, else do weather. So that means suppose there are 10 process and x-axis is actually 5. Okay, so roughly 4 process will do. Suppose rank start from 0 to 9 and this x-axis is 5. Then what will happen? 0, 1, 2, 3, 4. So they will do ocean and rest 5, 6, 7, 8, 9 they will do weather. So suppose x-axis is equal to 5. So suppose there are 10 process and x-axis is equal to 5. Then in this way you can divide the whole and you can emulate MPMD, multiple program, multiple data. So multiple program means this part of program will be executed on suppose one set of processor, and this part of the program will be executed on different part of processor. Okay, so this part of the program will execute on different process. So this part will execute on some process, this part will execute on different process. So in that way you can differentiate which part of the program will execute on what process or what processor, that you can define. So in this way, multiple program, multiple data also you can simulate. Message passing are packet data. So in general message passing we know. So whenever we send message from one process to another process, so what we need to do? So sending process, okay, source locations, okay, sending process, receiving process, source locations, destination locations, source data type, and source data size. These are the 7-8 things we require. So whenever we're sending any messages, okay, so who is sending, who is receiving, so what are the source locations, what are the destination locations, what is the destination data type, what is the source data type, what is the data size, and what is the destination buffer size. So destinations database. So these are the minimum informations we require in the message passing system. And the message passed through communication network, and if in the same process, same processor or same message, it is also communication network, or without using also communication network it can do, okay, within the same message. Because within same message it actually passes through localhost. Okay.
Excuse me, sir.
Yes, sir.
Sir, what do you mean by ranks here?
What
do you mean by ranks here? That is the ranks.
Ranks means in MPI program what we do. So whenever we compile a program, okay, so compile and run the program. So SAM program, suppose MPI run a.out, okay. Whenever you do, it run for one copy, okay. So a.out program will run for one copy. But whenever you do MPI run minus NP4 a.out, then this a.out program will create 4 copy of the program. Well, that means 4 process will be created. And these 4 process have actually rank. One process will get rank 0, other will rank 1, other will rank 2, and other will get 3. So this 4 process will get different rank. So whenever we're running with many process, so every process will get 1 rank. Is this clear?
Excuse me, sir.
Yeah.
If we ask to create 4 processes and
Yeah.
there are only 2 processors available, then will it still happen parallelly or it happens sequentially?
Logically it happens parallelly, but internally it will happen serially, one after another. So 4 process will run on 2 processor. So in your laptop also, suppose you have 4 core, you can create 10 processes or 15 processes. More than number of processors also you can create. Anyhow, we can run multiple processes on underlying hardware. This is highly abstracted. Okay, so there is no issue. Is this clear?
Sir, in the next slide, in message passing, hello,
Yeah.
Sir?
Yeah, audible.
Yes, in next slide, it was written that we have to sign the destination location. So how do source determine the destination location for another process?
Not source determined. So in the code itself, we need to write that who will be the destinations. So that will come to that your questions. Okay, so I will answer that question. Okay. So this in message passing, this sending process, receiving process. So whenever you are doing sending, that we will discuss with examples. So that will be more better. So a sub program need to be connected to a message passing systems. Okay, whenever you do MPI programming, and a message passing system is similar to the online mailbox of fax machines and MPI. So program must be linked with MPI library, and program must be started with MPI startup tool. So what I am saying MPI startup tool means MPI run. So whenever you do MPI run in single PC, so MPI. So let me show these things. So whether in the last class I have shown these things. So whenever we did that thing, so this thing. So this MPI run. So MPI run minus NP4 dot slash hello MPI. In this case, the MPI run is the running environment. Okay, so we are running the hello underscore MPI program under the MPI run environment with 4 processes. We are creating 4 processes. 4 copy of hello underscore MPI will be run. Okay, so this is on single machine also you can do. In your piece, laptop also you can, laptop or desktop you can do. So you just install the OpenMPI, apt-get install OpenMPI, and you can run your compile and run your own program also. This is not difficult. Okay, and MPI program must be linked to the MPI library. Then only you can run on multiple machines. So this already setup kind of things already done. Whenever someone installed the or created a bigger system like permissions, they generally install all the things. We need to write programs, okay, and we need to run on top of MPI. Hello. So what is message passing? So ultimately, it is a data transfer and require cooperation of sender and receiver, and cooperations not always apparent in the code. Okay, so sometimes we need to look at very carefully. Okay, and let's see how it can be. So the message passing may be blocking. The program will not continue until the communication is completed, and non-blocking means the program will continue without waiting for the communication to be completed. So this is basic blocking and unblocking things. And in MPI, it supports both blocking and non-blocking. But in our basic example, we will look at only blocking call. Okay. And feature of MPI, if you look at in general, communications combine context and group of message security, and thread safety cannot be assumed for the MPI program. So why we are saying thread safety cannot be assumed for the, we are writing the program, how we'll distribute the data, how we'll share the data, that we will ensure. Okay. Some part MPI will answer, but we need to answer ourselves. And feature that are not part of MPI is process management, remote memory transfer, creation of thread, virtual memory. It is not part of MPI. So MPI will create separate process. Okay. And this process will be managed by our operating system. Okay. So it will not do anything. So virtual memory, process management, remote memory transfer, it will not do, MPI will not do the work. It will simply means what I can say, engage the OS to do the work. Okay. It will give transfer means control to the OS, and OS will do the management. MPI provide only powerful, efficient, and portable way to express the parallel program. Okay, so MPI was explicitly designed to enable library which eliminate the need of many users to learn much inside of MPI, how data is getting transferred, how process is getting managed. So many things we don't require to, how data is going through the network. Okay, so that we don't need to look at. So at high level, so we have many processes, and processes they communicate among each other to do a bigger work. Okay, so internal we don't need to do. Okay, so at high level we just assume that there are many processes. So as a user I will create many processes, and using these many processes I'll try to accomplish a bigger work. So that is my goal. So as a user, this is the goal. Just like similar to means what socket we do or file. So whenever you say file, whether file is means you are writing this file to a hard disk or SSD, or you are writing to a file to a means other memory, means CD drive or any other places, or sometimes what we do actually, we think of network, any device as a file. Okay, so file is very abstracted thing. So we use read and write system call to write to this destinations, and destination might be any. User don't know. Internally, OS and kernel will take care of the things. Similarly, so whenever we are writing parallel programs, so user should not know internal details. Without knowing internal, he should be able to write parallel program using multiple processes, whether it run on one machines or multiple machines. That also should not care. But at high level, he should be able to specify on which machines he want to run, on how many machines he want to run. That is the difference. And it is portable. Good way to learn about ourselves. Issue in parallel computing. So this is a unnecessary. If you deal with networking and OS things, then we will not actually be able to write a parallel program. So ignore the concept of actually OS and network. So we assume that there are many processes. We want to create many processes, and we using that processes, we want to accomplish a big amount of work parallelly. Okay, and this process will run parallelly on some underlying hardware. Okay, and that underlying hardware may be one laptop or two PC or multiple PC or for a machine, much bigger one. Okay, so how big the MPI library? So MPI library is actually huge number of functions. Actually, it built on C++, mostly C, and basically it has 6 basic functions. With 6 or 7 basic functions, 10 functions, we can write a very good parallel program. We don't require many libraries. Only 6 functions is more than enough to write basic functions. Another thing is some standard functions are there. So using that, we can write very good MPI program. And there are how to install MPI, that thing. There are 2 MPI library. One is LAM, local area multiprocessor, and other thing is MPI CS. This is Argonne National Laboratory. Argonne National Laboratory is one of the best laboratory. They actually have published very good paper. Also, they have designed the MPI CH. And on top of this, we have Open MPI also. And this is basic skeleton of any MPI program, just like Hello.c program. Okay. So whenever you write any C program, we include stdio.h. In this case also, what do we need to do? Include MPI.h. And void main, this is int argument and this thing. And this is MPI init, ampersand argument, argument say argument b. So this is MPI init, it takes care of many things. Okay. So it takes care of many things. And then MPI finalize. So this is very basic skeletons. Okay, MPI init and MPI finalize. And on top of that, you can put printf, scanf, anything you can put. Okay, suppose you put a printf statement inside the program. Suppose what you do. So this is basically detail about MPI init. Initialization of MPI init is the first routine to be called. MPI init is called once. So whenever you do na, so means all MPI. So MPI underscore whatever the functions, whatever you do, MPI library functions. So they execute collectively. So particularly MPI underscore init, MPI finalize, they execute collectively. And whenever but MPI send, receive, they executes individually. But MPI init, these are the global functions that they execute collectively. Suppose this is the program. So print hello world, and you try to run on 4 processes. You compile the code and try to run 4 process hello.mp, hello underscore mp. Then 4 copy of hello mp process will run. And every process, so if you look at printf, MPI init will execute once, MPI finalize will execute once. They are collectively they will execute. But print hello world, this is the local to the process. Printf is local to the process, and it will execute for all 4 copies. It will execute. Okay, so all non-MPI routines are locals. Thus, printf run on each process. Okay, so MPI functions return error code or MPI success. So this is the very basic of any MPI Hello World program. Okay, and on top of that, this is a little bit of improved one. So what we are trying to do in this case, MPI underscore com underscore rank, MPI com world. This is the standard keyword kind of things. Okay, and in this case, underscore rank, and in this case, MPI com world, what MPI com size, ampersand size. This program will tell. So what is how many number of process on how many number of processes I am running the code, and what is my rank. Okay, so if you run this code, then suppose you are running on 4 processes, then size will be 4 and rank will be different for different processes. So rank will be different for different processes, but size will be same for all processes. So suppose I am 0 of 4, 1 of 4, 2 of 4, or 3 of 4. So it will be printed like that. So MPI comp rank will decide what is my rank. Okay, so process its own rank, and MPI comp size what is the total number of process. So in OpenMP also we did, no? So thread ID and num thread, OMP num threads. Similarly here size is okay. MPI com size, whenever say ampersand size, the size will get the value total number of process, and rank is what is the my rank or what is the process number I got or the process got. Is this clear?
Excuse me, sir.
Yeah.
Sir, suppose in MPI I want to suppose utilize multi-threading in a particular single process. How will I do that in MPI?
So that also you can do. So
Okay,
using MPI means you can do. So within that code, you write multi-threaded code or OpenMP code.
okay,
You call a local function.
Okay.
You call a local function.
So MPI does not provide any support for multi-threading. It just duplicates processes, right?
Yeah, it duplicates. It is much higher level as compared. It is distributed memory model.
Okay, sir.
MPI creates separate processes. Okay, inside a process you can have multiple threads. You got my point?
Yes, sir.
Okay. So what are the basic communication construct? So the default communicator is MPI com world. So MPI com world, this is the default communicator or what is the backbone of communications. And a process is identified by its rank in the group associated with the communicator. So suppose you are running on 4 processes, then total size will be 4 and each process will get a rank. A process is identify its rank in the group associated with the communicator. And 2 important questions that arise early in every parallel programs. So how many processes are participating in the competitions and which one am I? So definitely this is how many processes means size. Okay. And other one is my ID. Okay, rank is my ID and size is how many are participating. So clearly this thing already have sense. MPI com underscore size report the number of processes. MPI com rank report the rank in number between 0 to size -1, identifying the calling process. Okay, so on which process we are running there, and every process will get its own rank. MPI data type. So the data message which sent or received each address means described by a triple, that is address, count, and data type. And the following data are supported: all predefined data type of C. Okay, and then array, subblock of matrix, and any other defined also we can it supports. And this is a very simplistic things. So we have many blocking and non-blocking one, but we will look at only blocking send, and we'll have example of only blocking sends. So if you look at MPI send, so it have start. Okay, so from which well, this is the source address. Source address means suppose process 1 data from which data means suppose this is start of the data start from this process. Okay, so every process, suppose MPI send means a process one will send to process 2, suppose. That means process 1 have actually address space, separate address space, and from the start location of each address space, process 1 address space, it will take the data. How many data? Okay, and what is the data type? And then it sent to destinations with tag. Okay, tag is just identifying. So this message buffer is described by start. So message buffer is described by start, then count and data types, and destination is rank of the target process in the defined communicator, and tag is the message identification number. So tag, it identify the sequence maybe or identification number of that message. Okay, a process may send multiple messages to means same destinations. So in that way, tag helps. Receive similarly. So on the same receiving process, where it get means need to be stored. Okay, and then count from which source, what is the data type, tag, and this is the status. MPI comes status. So this is a source can be wildcard. So MPI any source, or tag can be any tag. This also can be defined. Is status. This S is status, used for extra information about received message if a wildcard receive mode is used. Okay, if it is status message. And if the count of message received is less than the described by the MPI receipt command, the message is successfully received, else this considered buffer overflow error. So this is a internal thing, but in general, whenever you write, we generally cross check. Whenever you are sending, the same amount is getting received or not, also we can cross check. Similarly, in this case also, in MPI program, it involves multiple processes and they do send and receives. So here also deadlock may happen. Okay, so this is process 0 and process 1. Process 0 sending to 1, and then receiving from 1, and this send to 0 and received 0. So in this case, if it is blocking, then it may happen, deadlock may happen. Okay, send, this kind of things may happen. So this is called onset because it depends on availability of system buffers and block wrinkles. Because it two processes they involve using send and receives. So it's our who is writing program. He need to ensure that deadlock will not happen, because this thing will actually send message. It's through communicator, okay, and OS will not handle this thing. Send and receive message will be handled by MPI, and MPI program writer is responsible that deadlock will not happen at high level, MPI level. And what are the major collective communication construct? What is the collective communication construct? So it is not one-to-one. Every process will, what I can say, participate in the communications. Every process will participate in the communications. That is called collective communications. So collective communications, they are optimized communications routine involving a group of process. Collective actions are over communicators, and synchronizations may or may not occur. All collective operations are blocking. Okay, so everyone need to be finished, then only it have no tag. And with example, I'll show you what are the collective operations. Okay, so we can say broadcast. So suppose one process want to broadcast a data to all other processes. That is collective operations. Okay. Then gather, broadcast and reverse of broadcast is gather. So get some data from all the process and gather something. Okay, and collectively get some meaning. So this is gather. And receive buffer must have exactly the same size at the send buffer. So this is the all collective operations it have the property, otherwise you cannot do. And what are the collective operations are there? So very simplistic examples I am saying. So MPI broadcast. So this is the, whenever you say MPI broadcast, that means all collective operation of broadcasting and collective operations, all process must call the collective operations routine together. What we are saying, all processes must call collective operations together. So this is a must thing. And with example, it will be more clear. But let's see what are the collective operations. So this is broadcast, MPI broadcast. So in this case, so suppose this one, this process want to broadcast this 3 data RED to rest of the process. And what is the rank of this process? This is 0, 1, 2, 3, 4. In this case, this rank is 1. Okay, rank of the sending process is root process. Okay, 1, whatever putting, and must be given identically by all the process. Okay, so MPI broadcast, who will broadcast, that thing will do. Okay, and what is the, from which address it will take? Okay, not the rank address, and then how many counts, what is the data type? Okay, and this is the communicator. So MPI broadcast will do, in this case, before broadcast, it is available in only one process, this RED data. After broadcast, it will go to the all the process. So broadcast means clearly, suppose this is another way of doing. So P1, P2, P3, and P4, there are 4 process. And suppose P1 broadcast ABCD. Then after MPI broadcast, all the places, P1, P2, P3, P4, all the places, this ABCD will be available. This is the MPI broadcast. MPI scatter. MPI scatter. Scatter means it divides the things into different locations. Okay. So clearly ABCD, so before, if you look at the diagram, so it will be more clear. So suppose before MPI scatter, so ABCD are in this process, process 1, and after the MPI scatter routine, so it get distributed to all the places. A get distributed to 0, B get distributed to B, C get distributed to means 2, D, and E similarly. Okay, so this is scatter. So scatter means from which buffer of this route, then count, then data type, then receive buffer, then receive count, and then MPI data, receive data types. So these are the standard, and from which route we are sending. MPI scatter. So MPI scatter means, so clearly, suppose this is the process 1 want to send this data using MPI scatter, then it will get distributed ABCD. But here still, because it is in the SAM buffer, so BCD will still stay in the SAM process. Okay. Is this clear? MPI scatter is clear. MPI gather, MPI scatter, and MPI broadcast. So
excuse me, sir.
Yeah.
Does this scatter be random, or we need to assign to, like, to which process which data need to go like that? Or it's completely random?
No, not random. So scatter means all the process will involve in these communications, not means a specific one. It may go internally random, but all process get involved. Ultimately, everyone will get the informations finally, but how internally it will do, we don't know. Are you getting a point?
Yes, sir. It's like internally it will be done. We don't know what internal details or something.
We
like
don't know
that.
internal data, but whenever you call scatter, so it will send part of data. So based on our specifications in this case, okay. So in this case, we are scattering means one data to each process. Okay, and how internally it will do, we don't know. But after getting the means MPI scatter means routine. So because all 5 process in this case will participate in MPI scatter. Okay, so it is by default they will participate. So whenever you're writing MPI program, so and you are using means this MPI scatter gather collective communication, then everyone will execute at the same time. Okay, MPI gather. So this is also similar things. It's just a reverse of scatter. Okay, MPI gathers. So what we are getting? So before gather, every process have one data, and we are getting all the data and gathering at one place. MPI gather. Okay, so MPI gathers here. In this case, process, every process P1 have A, P2 have B, P3 have C, P4 have D, and after gathering, so P1 have all the data. One have all the data. Maybe so. In this case, still this ABCD will be P2 have still B, P3 have still C, and P4 have still D. So unless it is erased, still it will be there. So, but on P1 we'll get all ABCD. And once you get the ABCD, then whatever operations we want to do with ABCD, we can do. Then this is gather all. So gather all means, so replicate P1, P2, P3, and P4. Okay, so all are at different places. MPI all gather means all the places all will be replicated. Okay, so that means P1 have ABCD, P2 have ABCD, P3 have ABCD, and P4 have ABCDs. So these are actually means sending all data to all. Okay, so kind of thing. Everyone have all data. So earlier P1 have A, P2 have B, P3 have C, P4 have D. But now all P1, P2, P3, P4 all have ABCD. MPI all gathers. So suppose you want to do a work collectively, then this kind of operation is required. And MPI provide this kind of operations, collective operations, and it makes easier for means write MPI program or do the big work collectively very easily. And MPI provide another thing is called reduction operation also. So what is the reduction operations? It perform a global reduction operation across all the member of the groups. Suppose you are doing simple operations. Suppose O is associative operation. Some associative operations may be sum, maximum or minimum, or any user-defined operations also you can do. Suppose you are doing summations. Okay, so let's see some examples of maximum or minimum. So MPI reduce. Suppose do MPI. Suppose this is the ABC, DEF, GHI, GKL, and MNO. ABC is in process 0, DEF in 1. These are the GHI in 2, JKL in 3, and MNO in 4. And if you are doing, suppose one MPI reduce on first data, then A, operation D, operations G, operation J, operation M. So first data of this one, 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 and first data of this one. A, D, G, J, and M. So we are doing operations. Suppose you are doing addition operations. This operation is additions. Then what will we are getting? Addition of all first data of all the process. What are we getting? Addition of all the first data of all the process. That means summation of AIU we are getting. This reduction operations in have you heard about in machine learning we have MapReduce? Okay, reduction means from all the process collecting the data and doing some operations. Some you can do maximum or minimum operations also can do. Not only the sum, but maximum or minimum operations also can do. So D max, G max, J max, M. Then what will be the maximum overall A, D, G, J, M will get. So that operations can be sum or product or maximum or minimum or any user defined operations also you can do. And this is MPI reduce. Suppose example P1 have A, P2 have B, P3 have C, P4 have D, and we want MPI reduce on addition sum operation, then P1 have A plus B plus C plus D. And we have all reduce also, not only this simple reduce, but we have MPI all reduce also. Okay, so MPI all reduce will do for means all places summation will get. Okay, so kind of thing after reductions we have broadcast to all the places. Another operation is MPI scan. So MPI scan. So what it will do is scan one element from all the guys, all the process. Okay. So A scan, D, then D, G, then G, J, and M. It will be done in parallel, MPI scan. So if you have done any prefix operations, do you know? Prefix operations. From the student side, have you heard about the term prefix?
Yes.
What is that prefix?
So prefix is the beginning of any like the first part, the starting part.
Yeah,
When you
beginning of the first part. So in this case, what I am saying is prefix means, so suppose we have data means A, D, G, J, and M. So at each point, so this is suppose a 5-point version. At each point, we want to calculate operation up to that point. So here operation up to that point is A. So for this process, operations from A, this process and this process, A operation D. Suppose addition operations. So this operation is additions. In first process we have A. Second process what we have? A plus D. Third process we have A plus D plus G. So summation of 3 data. Here summation of 2 data. Here summation of 4 data. Here summation of all 5 data. So this kind of operations is called prefix operations. Okay, so at each places we are getting prefix operations. Suppose given a array X, okay, suppose X have means values means xi. Okay, suppose array X have value xi, and we want to create another array. Suppose yi. Suppose another array y, where yi is means value is this kind of things. Suppose X is equal to, so suppose I don't have, let me just connect the writing pad. Let me connect the writing pad and I can write. Suppose it's not getting connected. Suppose X is equal to means suppose X is a array. Okay, so X is a array and X is equal to 2, 5, 7, 8, and 3, 6. So this is the array, and we want to create another array. So where this value is sum of previous one. This is 5 plus 2 is 7. This one will be 14, and this one, so up to this. Okay, 5 plus 2 7, 7 plus then 14, 14 plus 8, how much it will be? 22. This one we want to put 25, and this one we want to put 31. So this one is actually prefix sum. So at each point, so we have the prefix. Okay, so prefix sum is very good examples in all parallel program or parallel algorithms. So many people they use. So MPI Scan is very good what I can say collective operations to do the prefix operations. Let's see what are the operations we have collective operations have heard. So one is first thing is send and receive we do, then collective operations, broadcast, okay, scatter, gather, all scatter, all gather, then reduce, all reduce, and scan. So these are the how many operations? Clearly you can say very less number of operations. So send, receive, broadcast, broadcast, send, receive, scatter, gather, all gather, reduce, and scan. So these are very simplistic 7 or 8 collective operations. If you know how to use this, then you can write a very good parallel program on Parmesan kind of machines also. And this is summation of n data. Suppose very simplistic example is summation of n data. So what master process will do? So we are trying to simulate the MPMD model. So multiple program, multiple data. So that means based on the rank, what part of the program will execute, that will decide. Okay, and we'll write on our own. So master process. So data to be read from the process 0 or from the master. Divide the data into n by m chunk size. Send the respective chunk to data to other process. Do the local sum on each process, and master also do, and receive the sum of other process and calculate the final sum. And what other process do? Because master process is responsible for these two. Master process is responsible for receiving sum from all the process and calculate sum. Then this is the getting the data from the keyboard maybe. Okay, and divide the data and send the data to all process. So there are master is doing send to all the process and getting data from all the process. And what the other process are doing? Suppose master is 0. Suppose you are involving 5 process. So master is 0 and 1, 2, 3, 4 are the worker process. Okay. So 1, 2, 3, 4 are worker process. So master also doing work, but he is coordinating, but he is sending work to 1, 2, 3, 4 also. So other process receive data, do local sum, and send the local sum to master. So this is the things. Let's see the code. Whether sum is there or not, I don't know. So are you able to see the code? So here what are declaring is upload data size. Okay, and then so this is MPI com size. This number of taxes we are getting, and then in this case, if master ID, then it is initiating the data. Okay, and offset is doing chunk size, and then for every destinations number of taxes from 1 to number of taxes. Suppose you are creating total 5 process, then 1, 2, 3, 4 up to 1, 2, 3, 4. That means 4 and master is 0. So it sent this thing. What sent? First thing is offset. What data you want? Every process have this data. Every process have the data, but that is local to them. Master will create the means what will be the content. Master will create what will be the content in that array. Okay, and then after getting the content, it will send. It will send what is the chunk size and what data need to be. This is first thing. How many data it says, and this is the actual data sending. So this is offset. Offset from offset. This values one data will send, one integer will get, and after that chunk size of MPI float. Okay, this many float chunk size amount of float will go. Chunk size amount of float will go to the destinations. Okay, so after that what it will do? So it is sending one after another. After that it will do its own work. That means it will do sum on its own area. Suppose total size is 100, total array size is 100, and 2020 we are dividing. 5 processes are creating, 2020 we are dividing. So this is master is doing its own area. So 0 to 20 area, and 21 and other process they will do on their own area. If tax ID is greater than master, then first get the data, first get the offset, how many data, and then get the data and do the local sum, and then send offset and send the data. Okay, so this is they are doing, and every process are doing the reduce. This my sum and sum will be reduced. So if you look at In this case also we are doing reduce. So this is the collective operations. Every process, even master and other process also get involved in this reduce communications. So once they get the local sum, my sum, local sum, so they do the reductions operation. Reductions operation, if you look at in master also it is performing, and it is getting performed in all non-master also, all other worker also. This is the where this local calculation is happening. This is on other process, and this my update in this same process also it is doing. Master process also doing. That means master process he is also doing. First he is sending the data, then he is doing on its own area, then he is receiving from means this is wait for receiving the data, and then what trying to do reductions. Is this clear? So collectively we are doing a means summation of n numbers.
Sir, here master will be the first process that is created. The default it can be any random one.
No. So the system will create, suppose you are running using 10 process, okay, or 5 process. So 5 process will be created, and one will be designated master and other will be designated worker. Okay. So who got the code? Means this is rank is 0. In that case, if rank is 0, if then that means if tax ID is equal to 0, that means rank is 0, then this part of the code will be executed in the master. Because this part of the code, because if rank is equal to 0, then only this part will execute. Master will execute this part of task, and rest of the guys, they will execute this part of the code. If tax ID is greater than master, that means greater than 0, then rest of the worker, they will execute this part of the code. Whenever you are creating 5 process, means system will assign one rank to each. And once after the rank assignment, they will start their work.
Can you share these codes as well, sir, along with the slides?
Yeah, we'll share the code. I'll share the no.
And sir, can we use the same tag twice, like the tag 1 and tag 2?
Yeah, you can use same tag twice. There is no issue, but message may get jumbled up. Okay, so next one is matrix multiplications. So very simplistic examples. So work get divided based on rows. So C is equal to A cross B. Yeah.
Sorry to interrupt, sir. We have class at 4, so.
Yeah, so that's fine. So we'll meet at around 6. So please log in before 5 or 6 minutes. Okay. So your assigned group. So I'll send email to you people.
Thank you, sir.
Excuse me, sir.
Yeah.
Sir, could you perhaps take a small doubts class before the quiz on?
I am taking regularly live sessions.
Okay.
So yesterday I was planning to take, but I got some meeting, so that's why I was not able to do. But maybe before the mid semester, definitely I'll do.
Okay, sir.
But anyway, I'm taking live classes regularly. So whatever your doubt, means you can ask any day.
Sir,
And
I
even
have
when
out in
you can mail me.
Achha,
You can
okay.
mail me in chat box also. You can write. Definitely, I reply to in chat box also.
Sir, I just had one small doubt in roofline model. Can I ask now?
Yeah, you can ask.
So in roofline model, wherever we use the bandwidth BS, it's written next to it that we use the bandwidth of the slowest data path utilized. What does that mean, sir? Why do we take the slowest data path utilized?
Slowest means suppose data is coming from long distance.
Okay.
And from long distance, ultimately bandwidth it depends upon the slowest pace. So which place you are getting long.
No, but the thing is, if I am suppose I'm using L1, L2, L3 cache and then the RAM, right? And suppose I utilize L2 cache 90% of the time, and the rest 10% of the time I use the slowest data path, suppose the RAM. So then this BS does not represent the speed of RAM, does not represent the actual rate of how fast I can transfer my data to the processor, right?
Yeah.
So why do we assume the slowest only?
If the array size is much bigger, it is not fitting to your what I can say cache, and it is only streaming data.
Okay.
So whatever we gave examples, the for loop, so triad case, all the things, we assume n is very big. It will not fit into the cache.
Okay. But still, suppose I am using serial code, right? And then in the serial access, I go I from 0 to 100, suppose, even 1000 or 1 million. So in that, if my block size is 10, suppose, then 90% of the times, even then I will hit the cache, right? How even no matter how large my n is, right?
Yeah.
So why are we considering the slowest data path then?
Ultimately, we need to get data from the actually what I can say. Suppose you are getting data from the memory to the cache. Suppose.
Yes.
Okay.
Yes.
And for one what I can say hit one miss, you are getting 7 data.
Yes.
Ultimately, you need to get data from the memory itself.
Okay.
Memory need to supply it data.
Okay.
Are you getting what?
Yeah, so in general, how slow is my RAM? Like, what is the factor of like RAM getting slow as compared to L3 or L2?
So as compared to L1, it may be around 500 times or 1000 times also.
Hello, am I audible? Hello.
Yeah, as compared to L1, memory
Yes.
may be 1000 times slower.
Okay, so 90% to 10%, even in that case, that 10% is the bottleneck. Is that the case?
Yeah. So ultimately, you need to get it from memory.
Okay.
If it is streaming one, ultimately you need to get it from memory. So you'll not get here. Even if after getting the things, every one miss, you are getting another 8. But this all 8 need to get from memory. Memory need to supply.
Right, right. Okay, that is fine. Thank you. This is what I wanted to ask.
So see you at 6 p.m. or 5:55 p.m.